Yeah. Although we are doing ocean studies.
So in which city are you, John?
Yeah.
In which city of Texas?
I'm in the College Station.
College Station.
Yeah. So it's a small town, about 1 hour from the Houston. Just a college town.
Yeah, that's nice. I never been there.
Never?
No, I haven't.
So you've been to the Austin last time, yes? So we're 2 hours from Austin.
Okay. Yeah, in the past we had, I don't know if it is still that we have Texas A&M CONACYT collaborating projects. I don't know if it is still working, that possibility. I will check out.
So I think the
CONACYT is somewhere national. Sorry for interrupting you. CONACYT, well, now has a different name. It's CECITY, but it's like the National Science Foundation from Mexico.
Oh, we do have some. Last year we have some Mexican student come and visit us for the geochemical environmental research group. Okay. So here we're doing chemistry for oceanography and also doing the observation. So, for example, we have a text buoy system tabs, and so we have the glider and the HF radar operations. So
excellent.
Yeah, but I'm the only person in this group who doing modeling.
Okay.
Yeah, so I have some. So this is the R-CESM, and I also runs for the operational coastal ocean forecasting system, which we call around the Texas and Louisiana shelf.
Karina, is it time? I think.
Yeah, I think it's time. Okay. Yeah, I was gonna say that I will read your bio and you will see how many models Yoon has to manage. Lots of them. Okay. Well, I think it's time and we can start. Well, today we have Dr. Yoon Liu as our invited speaker. Dr. Liu is a research scientist at Texas A&M University, affiliated with both the Geochemical and Environmental Research Group and the Department of Oceanography. He joined the university in 2018 after completing his postdoctoral research at the University of Maryland. Dr. Liu earned his PhD in atmospheric and oceanic sciences from the University of Wisconsin-Madison. And his research focuses on coupled data assimilation, parameter estimation, climate coupling, and numerical modeling. Dr. Liu's work involves the system development of the online coupled data assimilation system with the fast ocean atmosphere model, the carbon in ocean land atmosphere data assimilation system, and the online ECDA system with the regional community Earth system model that he's going to talk about today. He also plays a key role in developing ensemble coupled data assimilation for the Department of Energy's Energy Exascale Earth system model, I guess, and maintaining and operating the Texas Louisiana Shelf Model Forecast System. We welcome Dr. Liu, and you can go ahead with your presentation. Thank you.
Thank you very much. Thank you very much. And hola, good morning. So thank you very much to have me here, and today I'm going to talk about our regional community Earth system model, which we'll call the R-CESM. This project is international collaboration. So we involved the University of China and Hengkai and Texas A&M on the leadership of the Dr. Pen Chen. We used to have an international laboratory for high resolution system prediction. And here, when we developed this model, but because of the relationship between China and the US, so eventually this laboratory was shut down. So, okay, so this is outline for my today's talk. First, I'll give an overview for the R-CESM system and then show some application for this system. For example, the Gulf of Mexico climate simulation and tropical cyclone simulation. Also use the R-CESM to investigate the deep dynamics related to the loop current eddy separation event. And I also introduce our online ensemble coupled data assimilation capability for the R-CESM. So R-CESM, we call it a regional version of the CESM. Its parent is the CESM. So we use the framework of CESM2, which have the framework actually different model components exchange information with the driver or the coupler. Then the coupler pass all the coupling factors to different components. So for our work, it's like build a regional version for the CESM. Then we introduced the WRF as an atmosphere component into the CESM framework, and ROMS as a land component into this framework. So currently we have 3 active components for the R-CESM. So for the atmosphere part is the WRF, land part is the community land model, and the ocean part is the ROMS. Because the CESM have the other components, so in the future it's more easy to activate those components to make this system more sophisticated. So when we want to build the WRF and the ROMS into the CESM framework, CESM calculate the atmosphere and the ocean fluxes within the coupler. So first thing, we have to bypass the surface forcing input and the surface out, see flux calculation in the ROMS and in the WRF. And also, then we'll send those surface variables such as SST and surface current velocity in the ROMS and send those to the coupler. Also, for both, also we send the bottom layer temperature, wind, and so surface downward radiation flux and surface pressure to the coupler. So the coupler will calculate the atmosphere and ocean fluxes and pass to the ROMS and the WRF. And that's we call this calculation, the LC flux, we call the CESM surface flux scheme. And this scheme usually is designed for non-climate simulation to study the large scale and low frequency climate dynamics. For those regional applications, we usually will face the other end, that's synoptic scale and the extreme event. So on the other hand, the WRF has its own built-in surface flux calculation scheme, which is focused on just like the extreme event, the synoptic event. So we also keep the WRF atmosphere ocean flux scheme within the system. So we have two choices. And here with it's a land component. Actually, it's because the CLM community land model actually is calculating atmosphere and land flux within the land. So the land will pass this flux into the couple and a couple of pass to the WRF. So I just mentioned that that's the two flux calculation scheme. This is the difference about the exchange coefficient using Bach formula. You see the solid line is for the CESM, the dashed line for the WRF scheme. The WRF scheme keep a cap for this coefficient when it faces the high wind, but the CESM scheme actually this coefficient increase with linearly with the wind speed increases. So currently we have configured two domains for this R-CESM. And one is for the Gulf of Mexico and another one for the coastal extension region. You all noticed inside the blue curve, inside the blue box is swarm domain, and the red one is a WRF domain. Because we said that one so WRF domain is slightly bigger than the ROMs. When we design in this way, it's like we can try to avoid the imbalance between the narrow boundary condition and the WRF inner basin dynamics. So which this one will not impact the ROMs domain. So we in that way we'll have a extended area which will provide the prescribed SST and blend with the ROMs output and then pass to the WRF. So some of the unique features for the R-CESM, that's firstly, we're using the CESM infrastructure SIM, and we have the full version the community land model. We provide two LC flux schemes, and also we'll have a online data assimilation capability. I'll talk about later for this part. So R-CESM and can be conveniently used as a regional dynamic downscaling tools for, especially for the global CESM. And then also it can be a standard non-high resolution regional coupling model. Because we're using the same CESM framework, actually it's very open for the community of the CESM communities. If you know how to run CESM, it's easy for you to catch up to run the R-CESM. Okay, now I want to show some of the application for the R-CESM. Since we have the system, first we want to know how good it's assembling the climate, because our original purpose to develop this model is to study the climate downscaling. So we conduct a 9-year round Gulf of Mexico simulation for the year of 2010 to 2018 period. Use the spatial resolution for WRF and the CLM is 9 kilometer, ROMS is 3 kilometer. The boundary portion, narrow boundary portion, come from the Copernicus for the ocean and the NSAP CFS for for the atmosphere. This time we're trying to show the comparison between the observation and the model simulation. The top panels are for the annual mean SST, and the left one is for Jia, the operation, AVH Jia SST, and the middle panel is for the model simulation. The right panel is the differences. Along this 86 west section, we also plot, after remove the annual mean, we plot the zero cycle of the SST for the operation and the simulation and the differences. The lower panels, we try to show the AD kinetic energy compared with the operation and the model simulation. You will see. So the model successfully reproduced the climate of the Gulf of Mexico in the ocean. Similarly, we can also compare the atmosphere variables. Here we use the precipitation. The panel A actually is the operation. For the land is, and the US land actually is, we're using the inset stage 4 product. The other region is trim, and this is operation, and the right panel is the model simulation. And panel C shows the difference. And panel D, we demonstrate the probability density function for daily accumulated precipitation. The black curve is for the operation. The red one is for the R-CESM simulation. So top is for the, I think it's NSAP, bottom is the other regions. The NSAP is for the US land domain. The other is for the, I think, include the Mexico and also the Gulf of Mexico ocean basin. Basically, this non-simulation and still we reproduce the climate of the Gulf of Mexico for both atmosphere and land. Another application is for the simulation of the tropic cyclones. So with R-CESM, we picked the 12 observed tropic cyclone within the Gulf of Mexico from 1995 to 2018. Since we're dealing with the tropic cyclone, we increased the atmosphere resolution from 9 kilometers to 3 kilometers. So initial condition and boundary condition come from the ERA5 and the Copernicus for the ocean. So each tropic cyclone event, we include the two sets of experiments. One uses off-surface flux scheme, and another one you see some surface flux scheme. Within each one, we wanted a single ensemble members. So this also shows the difference for this surface flux scheme difference for the jet coefficient. So this slide will show the result and the comparison for these two schemes. And this is a composite of this top panel, composite of the tangent wind speed in shedding and the secondary current in vector for the tropic cyclone peak intensity. Actually, this exponent is distant from the center. So we pick, once we get the peak intensity, we find the center and calculate around the wind speed. So for the neck, the top A is the CESM, come from the CESM flux scheme. Then the middle panel is the Wolf flux schemes. And the right panel is the differences. You will see clearly, but also we can zoom in to see the planar boundary layers. So making it more clear. You can see clearly from the amplitude. The warp surface scheme generate stronger wind, a stronger hurricane, stronger tropic cyclones compared with the CESM surface flux scheme. So it coupled with the stronger secondary current. This is a CESM minus warp scheme, so that's just the other direction of the secondary circulations. So with a stronger wind, actually it's caused a stronger sea surface cooling. So both have a strong surface cooling compared to CESM. Here we don't use because it's hard to do composite locations. So we chose the Hurricane Harvey in 2017. And this is the operation for the panel D. And this is both of the scheme generate stronger cooling compared with the operations. And the panel G, we show the ratio of the enthalpy exchange coefficient to the drag coefficient, which is supposed physically proportional to the maximum tangent wind. Actually, so this result is consistent with this wind because you see the ratio is bigger compared with the CESM. And the panel H, we show the scatter plot of the tropic cyclone maximum 10-meter wind speed versus the minimum sea level pressure. And the red is the warp scheme, and the blue is the CESM scheme, and the black one is the operation at the Gulf of Mexico from 1979 to 2018. See, the wind and the pressure relationship, the work scheme produced so almost perfect relationship compared with the CESM. This is not surprise because the warp surface scheme is focused on synoptic and extreme event. It's just so compared with the CESM surface scheme. So have some summary for this part. So first the message is like we reproduced the mean SAT, precipitation, and ocean eddy connected energy with our non-multi-year hydrogen simulation. So the tropic cyclone simulation revealed the warp LC flux scheme and plays better, actually kept the drag coefficient at high wind speed and yield stronger tropic cyclone intensity and more realistic surface pressure wind relationship compared with the CESM scheme. On the third part, I didn't talk with, I'm not talk about this part is we also studied convection permission simulation for the mesoscale ocean atmospheric interactions. Okay, you want interest about this part, you can read our paper at the bumps. So we're also using the R-CESM to investigate the role of the deep dynamics for the loop current eddy subversions. For this work, the hypothesis is the high frequency variation stimulated by the loop current can increase the instability, which has a positive feedback, trigger the detachment of loop current eddy. When the energy of this high frequency band surpass a certain threshold at the critical regions. So this work and the object for this book is just trying to establish the linkage between the lower layer process and within the low current system for low current eddy-shedding event. More specifically, we are investigating the middle wave 8 to 16-day mixed wave signal in low current eddy-shedding event within the R-CESM model. So this figure is trying to demonstrate the R-CESM on this questions. First, the funnels A, B are the main stage of the R-CESM, and the standard deviation of at 800 millibar. So AB. And the black vectors are the mean flow, and the shaded color is temperature. The black vector is the mean flow. And this green ellipse is the variance of the current. Contours, the white contour you will see is the axis of height, indicate the position of the loop current. And this variance. So we draw a box. This indicates the region for the loop current, the system dynamic. So we draw these two sections to show the vertical profile. And because we are talking about interest about the deep layer interacting with the loop current system, so we want to find the representative depth or the layer for this. So it should not be within the loop current system, but they're not far away. So usually we say that 6 degree comes at the bottom of the loop current. And so you'll see the potential density layer at 27.5 is just below this 6 degrees. And for two sections, and there was at a depth around 1,000 meters. So this will try to also show the topography for that, because that's important for this deep ocean variabilities. Okay. So this panel, I want to show this map. It's the mean distribution of the stream function at this potential density layer at 227.5 based on the distribution of the variance. So we selected 5 regions to do a wavelet to compare with operations. So this panels are the wavelet analysis for the operations for 3 introduced station, P1, C1, PN4 from the SAC and CSS. Yes, from one of the stations is yours. At the 900 meter depths. There also, this 3 station also included by the region 2, 3, 4. So the bottom, actually for each wavelet at the bottom, this is the time series for 8 to 16 band variance, and time series for this 80 band. So you will see at each major low current eddy-shedding event, they will have significant 8 to 60 band variance within these 3 observations. Similarly, so we do the same. And this is also shown in the previous studies. Then we apply the same wavelength analysis to the velocity for the 5 regions, except the region 1 or the other 3 regions was shows the significance 8 to 6 days variance before the major Gokhan eddy-shedding event in the model. So that's when we say our model did reproduce the 8 to 16 band variance happening in the observations. So this we're trying to track the temporal evolution at the 27 potential density layer depth and the strong relative velocity. So we draw the 3 sections in here and plot a moral diagram, show the variance of depths. So the shadow shows the 27.5 density layer, the depth, and which indicate the movement of the loop current. So this red and the blue color are the 8 to 16 day band relative velocity. It represent the propagation of this mid-wave mixed wave. Here we only keep 2 years, from 2012 to 2013 in the model. You will see every time when the loop current activates in the slope, you will generate 8 to 16 mixed wave, and then this wave propagate west or east. So we have 3 sections I forgot to mention. Actually, we're trying to represent 3 flow within this domain, Mississippi Fan and Yucatan Channel and West Florida export. So based on some of the observation for the animation and also the self-octant map, we set this 6 to 8 wave and into 5 scenarios. First scenario is we call the East Yucatan Shelf scenario. Happen that when the current is the early intrusion or retreat phase. So when the current interact with the Yucatan Shelf, it will generate the mixed wave, propagate around the low current. Total happened for this case is for our simulation 8 years already, 28 times. 8 of them is related to the major loop current eddy shedding. So the percentage is 28%. So second scenario is the west loop Yucatan channel shaft. So that's this wave, mid-wave propagate to the west when the loop current is west penetrating. So 4% of this when it happens with this kind of a wave trend will eventually relate to the loop current eddy-shedding. So also, okay, sorry. Third case is that we called West Florida escarpment and also the Mississippi Fan, which is more significantly related to the loop current eddy-shedding, and 72% of the situation related to the loop current eddy-shedding. The fact one is we don't have this for the situation we don't have 8 and 16 mixed wave. So by using, we talk about west neck down region, and we define a new necking down region in the west of the current system that can be by the spatial distribution of the 8 to 16 days kinetic energy. And it is consistent with those two scenarios. The area will connect to the Mississippi Fan and the Yucatan Shelf. We integrate the 8 to 16 days band variance based on the variance preserved spectrum of the average grade at 27.5 layers and to get this map. The highlighted region are the Mississippi Fan and the Yucatan Channel and the West Florida escarpment. Finger B, 2E, and are the variance preserved spectrum of those yellow dots in A from north to the south, which demonstrate the peak of the 8 to 16 days band. The figure F and G are the vertical distribution along these two yellow sections. One is for Yucatan Shelf, one is related to the Mississippi Fan. And it shows the relative distribution of the 8 to 16 days band variance at different layers. The 8 to 16 band variance are more dominant on the slope region at the lower layers. And the figure H and the I are the horizontal diagram of the 8 to 16 days band integrate power from their wavelet at each point along these two sections. For this three-shedding event, in these 2 years, they all started from the Yucatan Channel, Yucatan Shelf, and ends at the Mississippi Fan with a westward propagation trend. Okay. So, conclusion. So this one, this is first, this weather band deep signal is stimulated by the interaction between the loop current and the topography, then released from the topography as a free wave here. But the wave spectrum cannot identify as a mixed rush wave or wave, which we call it a mixed wave. And there's a 3 critical regions for this wave generation. So Florida escarpment, Mississippi Fan, and the Yucatan Shelf. And the previous cycle 5 defined scenarios can be used to describe the different stages of the current system from the bottom of the new current system. And also we defined a new western necking down region around 89° west by the 8 to 6 day kinetic energy at the bottom of the new current system, which contribution to the separation of the new current eddy without retouchment. Okay, so now I'm going to talk about the online ensemble coupled data assimilation capability for the R-CESM, which we developed. So there's a certain concept. First is the online, second is coupled. So online, for a regular data assimilation framework, for example, this is Ensemble Kalman Filter data assimilation. So for a regular one, actually the data assimilation and the model are independent. They exchange information through the hard drive. So model output forecasting as initial condition, restart file, and the data assimilation radio operations in this restart file, and we produce analysis as a restart file as an initial condition for model continuous forecasting. On this one, easy to implement, and but it's very costly for computational. It's generally intensive input and output to the hard drive, and also frequently stop and restart the models. So we come up with another idea. So we're trying to avoid this computation cost. So we're building the data assimilation into the model. So integrate the Ensemble Kalman Filter algorithm into the forecast mode as subroutine. Therefore, we can conduct the data assimilation online without stopping the model and output the restart files. So avoid this intense input and output and frequent model restart. So another concept for coupled data assimilation. So there's an uncoupled data assimilation. So data assimilation is conducted with a single model component. For example, animal data assimilation is used as model only, and the ocean data assimilation is used ocean only. When you want to do a forecasting use of coupled model, then you put this uncoupled analysis, data assimilation analysis together to generate a coupled initial condition to conduct the forecasting. This cause some inconsistent and dynamic because they are doing separately. For coupled data assimilation, actually we're doing data assimilation in the coupled model. So although you're doing data assimilation in the old ocean operation only constrained ocean, animals are still only constrained atmosphere, but this is within coupled model. So also have the strongly coupled actually use operation in the ocean to constrain the atmosphere and the vice versa. So our system is online coupled data assimilation. So to get online data assimilation is requires two things. Actually, firstly, you have to run the model ensemble parallelly, and secondly, you have to be able to let the ensemble copy talk with each other. We have to create a cross-ensemble communication. So in terms of computational efficiency, previously we test the data assimilation computational in our system is on the count on the total computing cost is 12%. If you use a regular data assimilation framework, actually it's about 3 or 4. That's cost more. It's a major computation cost. But here it's only counts on 12%. So this system is much more efficient. So so after this thing, we did some testing for the system using observed system simulation experiment. We have a total 4 experiment, a simulation SST only, a simulation surface head only exception. Both of them, we compare with that. There's 4 cases, so no data simulation, the RMSE for system height, mainly at the current variability region. Then you estimate SST, you slightly decreases, maybe 25%. Once you estimate the system height, well, it's dramatically decreased because you see the scale is different. You estimate both, actually comparable but slightly increased. So you compare when you look at the temperature, so no data simulation. Once you assimilate system's height, actually it's also dramatically decreased the temperature RMSE system asset temperature now. Yeah, some SAT, yeah, definitely FT is close to the truth, and also assuming both SATs, RMSE is dramatically decreased. So this is show the difference for the vertical profile for temperature and current. So I don't have time. I'll just maybe get to the This the end. Okay, maybe. So I have some summary for that. Maybe I don't have time to talk about that. It's the we have the online Ensemble Kalman coupled data assimilation capacity for R-CESM. In the ocean component with a very high computational efficiency, and we simulate excessive temperature and excessive ST, sorry. And SSH observation show a more substantial impact on the model analysis and the forecasting than the sea-surface temperature observations. And the analysis also show a clear seasonal dependence, and particularly for assimilate SST observations only. I guess I'll stop here. Thank you very much. And take questions.
Thank you. Are there any questions? Preguntas, pueden abrir su micrófono o escribirlas en el chat. Tere.
Yes, let me open my. Thank you, John. Very interesting talk. Since I'm an atmospheric scientist, I will ask about your results on atmosphere. You showed some simulations for Hurricane Harvey. I wonder, so the analysis was done on a climate or a forecast mode? That's the first question. And the second one is if you have done some evaluation with ERA5, for example, because you showed precipitation and winds at 10 meters comparing CSM and WRF. But have you done any other evaluation with ERA5? I mean, I understand that you have already some assimilation, but an external.
So for this hurricane simulation, we didn't conduct any data assimilation, and we call the hindcast because it's going to the past. We only can got the narrow boundary condition is from the real analysis, so it cannot count on the hindcast. So I'm not sure. Yes, this is pure simulation. I think we don't do any data assimilation.
Okay.
We do try to do the forecasting. But when we finished system, we did just one Hurricane Noracam. I think we did wrong forecasting mode to forecast in Hurricane Nora. That one is category 4 hurricane. Not needed on the Louisiana coast, I think, Alabama. But I'm not sure about that. Okay. So let me see. Do you have the forecasting there?
Yeah, my question was that if you evaluated with other reanalysis this particular case. I know that this high resolution, your results are high resolution, but still there are some regional circulation that possibly ERA5 can capture.
We didn't do further analysis for that work. This is why forecasting NORA using this. This is real forecasting because I did at the exact time.
That's pretty good.
Yeah, very old because this work finished very old at that time. So we finished this system and the Hagnola is coming, so we did a real-time forecasting. And you compare with, you see, the green curve is the National Hurricane Center produced best track. And the red one is our forecasting, starting from here.
Yeah, it's amazing.
Yeah. So the current track is matched very well, especially over the ocean. But overnight, it eventually drifted away. So in terms of the intensity, actually, this shows the top panel shows the maximum wind speed, and the bottom panel shows the minimum sea level pressure with time. But our model eventually forecasting is caliber 5, but the reality shows caliber 3, close to caliber 5. So the maximum sea level pressure is also deeper compared with the operations. Not, yes. That's because we just used the initial condition from the GFS and the Copernicus. We didn't do any manipulation, just put there with the data assimilation, which we call cold down, not warm down. Cold, it's cold start, no warm start. That's caused some discrepancy. Yeah. So
thank you very much.
Are there any other questions?
Okay.
Well, someone else asked another question. I think I missed what was the difference between the WRF flux scheme and the CESM flux scheme?
Okay, so I didn't show here is like we know when we calculate the flux is actually all of us actually use a Bach formula. But how to dealing with that is different because they have some details for the equation, how to derive those things. Here I didn't put in the details for that, or I only have the feelings because the CESM and the WRF actually derived from different branch. For example, I think Bill Nigel at the NCAR for CESM scheme, so they calculate. But for myself, I cannot explain the details for the equations, how they get one part and one another. And then we only know, but for CESM, the flux they calculate is really focused on for the climate simulations. Then tune everything, make sure it can produce realistic climate and the variabilities. So original the WRF itself have the surface flux calculations. Actually, the model it tunes using the approach and tunes to represent the synoptic scale and the extremely event sense. You'll see they are different if you can compare with the equations and the approach they get at. I know both come from the initial box formula. That's true. Then you calculate this coefficient is totally different. So the extent coefficient for different flux is different, for example. So they have some consistency, and but you'll see the big difference is mainly happened for high wind. So when you dig into the WRF flux calculation, actually they set a cap. When the wind above at 30, above 30, so they keep this coefficient as a constant. But for CESM, we don't have this caps exist, so you will see these ratios. The coefficient keeps increases, even with you suffer with a very high wind.
Okay.
And as you know, when we run in the global CESM, the wind cannot go that far. You cannot generate, especially for the coast resolution, the 10-minute wind speed will never reach to 70 to 80. Yes. But when we put into regional couple system, we still use this one, this dot. This one is still valid and is still to represent the extreme event and the synoptic scale weather phenomenon. Okay.
Okay. Thank you. Is there any more questions?
Yes, Karina, me. Can you hear me?
Perdón. No te
Yvonne.
Yvonne, yes.
Yes. Hi, Jun. Thank you very much. It was a very interesting talk. There is, you probably know, but there is a lot of people in here right now working on couple models, data assimilation systems, and also now trying to do some forecast for tropical cyclones. So there is a lot of questions that I have, but maybe I can just limit myself to a couple. The first one is actually in this slide. I wanted to ask you about your line of thought regarding the selection for your domains for the ocean and atmosphere model. So the atmospheric one, WRF, is much larger. And I wonder if that's just because you wanted to see, you wanted to have the simulation for the land, or if there is any other technical reason why you extended the WRF domain.
Because we have a narrow boundary condition, actually it's not consistent with the WRF because it comes from outside. So usually the boundary will generate some fake information, and especially for weather, for the atmosphere, we don't want this turbulence impact the ocean. So in that way we make sure the boundary of the ocean the domain of the ocean is slightly smaller. So those boundary impact from the atmosphere will not impact the oceans, active oceans. At the same time, because ocean have boundary condition, but that's also cause some initial shock. However, that part, if the ocean boundary and the animal boundary are together, actually two kind of resource will also resonate each other with even worse result.
Right.
So that's why we set the X, we call that extended area for ROMs. So we call that X ROMs. That's we provide or prescribe the SST and the other things, and the blend with the ROMs output and together as a whole field to pass to the coupler and then pass to the WRF.
Right. And by the way, so by any chance, did you evaluate it, like the added value of having the coupled and uncoupled simulations for the same domain? Because I wonder if you were able to see an improvement in the coupled simulation.
Actually, I didn't. So
okay,
so
no, that's
some. I have a previous work on not on this model. We do have some model, so test this part, uncoupled, coupled, and how much coupled, and improve that. And so also people also work on the strongly coupled issues. We have the paper how to do the strongly coupled in the other models. So, and I think we had a paper reviewed about coupled data assimilation. So intuitively suppose the coupled model will provide more balance and the analysis reduce the initial shock. But I don't get a chance to compare this within this system.
Yeah, no, that's completely fine. I mean, one will expect that the coupled model is better, but it's good just to know how much better. The second one is
that depends because this is a very hard comparison. It's very hard to say it's apple compared to apple because for data solution, actually you change a little bit, you need to tune the parameters, and then which one you will see in this setting, it's perfect for coupling, but not perfect for the uncoupled.
Exactly.
So
yeah, that's right. And the second one is regarding a little bit more about the, so you didn't mention, for instance, the fields that you exchange between the ocean and the atmosphere. So I'm guessing it's like the typical, the current and the thermal feedback, right? So you're exchanging SSTs, currents, and then I guess evaporation minus precipitation.
yes, so here I'm not sure I read something. For example, to calculate the surface fluxes, you need a certain amount of the variables. For example, you need for CSM scheme, also for the WRF scheme, CSM scheme they require from the variable from the ocean is the temperature and the surface current. That's the two things we passed. For the ocean, for the atmosphere, in order to calculate these fluxes, we also need to using the downward radiation fluxes and humidity and temperature.
Right.
Yeah, and the surface pressure. So all those things can be set to pass to the coupler.
Right.
Anything, yes. The good things for this CSM scheme is either to add or remove one of the passing variables. And the other things, then the coupler handle everything to regrade, make sure the regrade make the grade is consistent, and then use the variable to calculate fluxes.
Right.
So if for the WRF flux scheme, we have to calculate in the WRF, then we directly pass the fluxes. And then the coupler will interpret it into the ocean grade and pass the ocean grade.
Right. And I guess it's the same for the wind stress, right? So it's WRF the one that computes it, and then it passes it on to the ocean model. Is that how it works?
Wind stress is calculated in the coupler.
Right.
Yeah. No, so for the original CSM framework, actually, LC, flux, everything calculated in the coupler. So it collect this required variables from the atmosphere and ocean and calculate it, and then pass back to each component. Then atmosphere and the ocean get the same fluxes.
Okay. Yeah. Exactly.
Yeah.
Yes. Coherence.
Yeah.
Okay. And if I may, last one, please. I think I was actually very interested in the last in the slide that you showed to Tere, the first question. So I just wanted to ask, in terms of the configuration, for instance, for tropical cyclones or hurricanes specifically, do you have a couple configuration that is available online, for instance, to see the parametrizations that you use and these kind of details? So, because I mean, it's very surprising that for a hurricane category 5, you really get almost like the wind speed and the mean sea level pressure. So the question is,
I don't have the configuration online, I think.
Okay. But
yeah, I didn't put it anywhere because.
Okay, that's okay. We can be in touch because it's just just to see the kind of I mean, what's the tuning that you use so that you could get like this very high wind speeds? Yeah.
We didn't tune too much things, I think.
No? Nice.
Yeah, we didn't tune much things, just using some of the default configuration in the WRF. Yeah. We cannot use all the WRF set schemes because we also have the boundary boundary scheme. I think we only can validate for several of them. But yes.
Right. Okay. Okay. Excellent.
So this is also we didn't have to. Yeah. See, this is the Hengkai, not I guess. So we did get a very surprised forecasting result.
Yeah. It's quite good.
Maybe it's been lucky because we don't have the manpower to continue to do forecasting for every hurricane coming.
Right. Yeah. Okay. Well, thank you so much. That's all for me. Thank you.
Thank you.
Por ahí había otra mano levantada, pero creo que ya no.
Bueno, a mí me gusta.
Felipe,
Hi.
adelante.
Yep. Hi, you. Thanks very much for your talk. Very interesting. I wonder if your implementation includes the Mississippi River output.
The question is, we don't have the Mississippi River output for the result I showed today.
Okay.
Actually, when I did add this part in our model now, when we configure these studies, we haven't added the river runoff into the model yet. But now we have the Mississippi River runoff into the R-CESM. But
Okay,
it's
so
not in a coupled way. It's like we prescribe the river run flow and input it into the model. And I know CESM have its own river runoff model, but we have some technical challenge to implement that. One thing is the ROMs don't have a capability to accept the river runoff in one grade point. But the POP for CSM, that the river runoff is actually coming with runoff is just put into one grade point. Then they have some adjustment, then model adjustment to make sure this fresh water can distribute to nearby grades. But the ROMs don't have this capability. So there's some technical issues we need to solve right now. So we prescribe the river runoff for ROMs.
Okay. So which version of ROMs are you using, if I may ask?
It's not a newest version, yes. It's suddenly out of my mind. What is the version? I already somewhere. So I cannot give you answer now. But it's not the newest version. We last time we tried to update the version, but we haven't done that yet. Yes. We don't know how much benefit when you update the ROM to the newest version for this CAP system yet. If you're interested, I'll go find out and tell you later.
Okay. Well, yeah. Thanks very much.
Yeah. Thank you.
Thank you.
Okay. Thank you.
Thank you very much.
¿Hay más preguntas?
¿Puedo hacer una corta?
Claro.
Sí. Hi, man. Well, sorry, I didn't understand so well how the couple works in the work from system. So, I mean, the couple is integrated in the component setting, or we need to make an installation apart from the work from ROMs. I mean, the question is for how editable is the couple for I mean to integrate more variables to be interchanged in the work ROM system.
The coupling, I would like to say major part is the exchange the fluxes between the atmosphere and the ocean for the ROMs and the WRF. Yeah. And so you make sure the WRF and ROMs use the same fluxes based on the dynamics. So if we're uncoupled, so this surface fluxes will generate by itself with prescribed, for example, WRF use prescribed SST, and ROMs use prescribed surface forcing. So for coupling, actually, so WRF use the ROMs SST to calculate the fluxes. So it's this is a high frequency, well, not high frequency, it's a time dependent SST. It generates dynamic. Generate from the ROMs. So in terms of this coupling, for example, if we say at a certain time, for example, company have a what called the first thing is coupling frequency. So for on which time frequency animals and the ocean exchange information. For example, it's CESM, I think it's 3 hours. So here, I think I said the company is half an hour or something, or less than that. That's a tunable variable. So to every hour, so water and the warmth produced is surface, like a temperature and wind. Then all those things will pass to the coupler in this system and use this one to calculate fluxes and then send it back the flux to the water and the warmth. And that way coupling is like a, how to say, water is the impact is water, right? It's passing through the warmth get this in the warmth impact and then generate the temperature. And then this temperature will feed back to the water. Instead of the SST, for even running water only, SST, how the variability of SST have no way to relate to the variability of the water.
Thank you.
Okay. Well, I think if there are no further questions, we can thank Yun.
Oh, thank you very much for having me. Yes. You have further questions or anything, please email me.
Thank you.
Thank you.
Bye.
Thank you.
Gracias a todos.
Bye.
Gracias.